Hey doctor, my name is Catherine and my matrix number is 22086424.
Hi, I'm Nada Amalia Patricia binti Muhammad Ahi with matrix number of 22001524.
Hello doctor, my name is Danisha Zakaria and my matrix number is 22000598.
Hi, I'm Sharawi Zamshuri Bintani Zamshuri and my matrix number is 22000952.
Assalamualaikum and hi, I'm Nur Kistina binti Muhammad Sani, matric number 23005-157.
Statics and mechanics disciplines form the background of our understanding of how forces and moments interact with structures, shaping their equilibrium and motion. Statics, the study of objects at rest, delves into the analysis of forces and moments acting on them. In contrast, mechanics expands this analysis to include objects in motion, unraveling this intricate relationship between forces, mass, and acceleration. In our exploration of statics, we consider structures as rigid bodies in equilibrium, vital for preventing deformation. Understanding the forces applied to these structures is crucial, especially in the context of a reciprocal walker. Friction, a key player, is classified into fluid and dry types, with our focus solely on dry friction. As we analyze the reciprocal walker static friction force, we witness its increase with external force until reaching a maximum value determined by the coefficient of friction. This force dynamic shifts to a kinetic friction force when the walker begins to move, adding a layer of complexity to our understanding. Considerations for the walker's mass, weight distribution, and support design significantly impact frictional forces. These forces are not just technical details but are essential for maintaining control, preventing uncontrollable sliding, and ensuring a safe user experience. Moving beyond statics, mechanics reminds us to account for deformations under axial loading. The stress-strain curve provides insights into material behavior, guiding our understanding of tensile and compressive stresses. In the context of a reciprocal walker, this knowledge becomes paramount, ensuring the structural members withstand loads without compromising user safety. Through individual analysis and collaborative exploration, we aim not only to grasp the theoretical foundations of statics and mechanics, but also to translate this knowledge into practical insights for biomedical device design. The objective of this case study is to demonstrate static learning outcomes (LO) using real-life examples. The first LO is to use free body diagrams to perform equilibrium-based analysis for various structures. Second LO is to solve problems involving a body under the action of axial, bending, and torsional load. The third LO is to employ moment and inertia-based analysis for problem solving due to compound load. The fourth LO is to evaluate stress and deformation of biomedical devices. And the last LO is to perform effectively as a team in analyzing real-life cases of static objects under loading.
So I'll be proceeding with the methodology. The first part is the forces acting upon a reciprocal walker. We have selected a reciprocal walker with mass 5 kilograms, and the vertical length of the walker is measured, which is Ly, from the very top to the very bottom of the walker. The horizontal length of the walker, Lx, is also measured from the right-hand side to the left-hand side of the walker. And a student of mass 60 kilograms uses the walker as shown in figure 6. And the weight of the student is determined using the equation W equals to mg, which is the force acting on the walker. The center of gravity is also assumed, shown in figure 6. The free body diagram of figure 6 is drawn showing all the forces acting on the system. A coordinate system and sign convention are recognized. Since the walker is stationary, the forces exerted by the ground, or also called the normal force, should be equal to the force exerted on the ground, which is by the walker and the student. And by using the equation summation of the vertical forces equals to 0, the value of summation forces exerted by the ground Fn is obtained. Moving on to the internal moments and forces in a reciprocal walker axle. So we know that the mass of the walker is 5 kilograms, and we also have measured the vertical length of the walker. The weight of the walker was also determined. So then a free body diagram of figure 7 is drawn showing all the moments and forces on the walker axle. The coordinate system and sign convention are recognized. Since the walker is stationary, the vertical force exerted on the screws F axle Y must total up to the opposite but equal to the force exerted by the weight of the student. The horizontal force exerted on the ground F axle X must also equal to the opposite of the horizontal force exerted by the student. By using the equations summation of horizontal forces equals to 0 and also the summation of vertical forces equals to 0, the value of horizontal and the vertical forces exerted from the ground Fxl y and Fxl x are obtained respectively. The moment M axle results from the student's weight acting on one of the axles, both horizontally and vertically, is calculated using the formula the summation of M axle equals to 0 after determining the sign convention. Lastly, the shear stress on bolts. We know the mass is 5 kilograms, the walker's mass, and the diameter of the bolt D is measured, and the circumference of the bolt C is calculated. The student of mass 60 kilograms uses the walker, as shown in figure 8, and weight of the person is determined using the equation W equals to mg. A free body diagram of figure 8 is drawn, and the coordinate system and sign convention are recognized. By using the equation area equals to pi r squared, the area of the metal being sheared A is obtained. By using the equation shear equals to F over A, the value of shear stress on bolts is obtained, and the value of shear strength on bolts is calculated.
Data analysis. Firstly, mass of the student M1 is 60 kg. Mass of the reciprocal walker M2 is 5 kg. Gravitational acceleration is 9.81. Vertical length between the top and bottom part of the walker Ly is 95 cm. Horizontal length between the left and right part of the walker Lx is 45 cm. Diameter of the bolt is 1 cm. Circumference of the bolt is 0.5 cm. Lastly, the weight of the student, also known as the force the object exerts on the reciprocal walker F person, is calculated with the formula F equal to mg. Thus, we will get F person as 588.6 Newton. Force act upon a reciprocal walker. Referring to the free body diagram in the figure, we already know that the sum of force of one axis is equal to 0. Two normal force minus force of a person is equal to 0. Force of a person is 488.6 Newton as we calculated before. Thus, normal force is equal to 294.3 Newton. Internal moments and forces in a reciprocal walker axles. Firstly, the sum of Fx is equal to 0. From the figure, we can see that F person minus F axle x is equal to 0. F axle x is equal to 588.6 Newton. Then, the sum of Fy is also equal to 0. And F person minus F axle y is equal to 0. F at ZY is equal to 588.6 Newton. Then, if we want to obtain F at Z, we use the formula square root F at Zx to the power of 2 plus F at Zy to the power of 2. Thus, we will get F at Z is 832.41 Newton. To get the moment of axle, we use the sum of m axle is equal to 0, and the positive is the counterclockwise. From the figure, we can see that f axle y, ly, plus f axle x, lx, minus m axle is equal to 0. M axle can be obtained, which is we will get it as 0.04 Newton meter. Lastly, shear stress on bolts. Firstly, we must calculate the area of metal being sheared using formula area equal to pi r2. With this formula, we will get area as 0.0785 square millimeter. Then we will calculate the shear stress using formula F divided by A. With this formula, we will get shear stress as 7,498.09 Pascal.
To continue, I'll be discussing on the critical topic of forces that may cause failure in reciprocal walkers and essential consideration for ensuring user safety and device longevity. So let's delve into the factors that contribute to potential failures in these devices. So as we explore the forces that may cause failure in reciprocal walkers, it's crucial to understand the impact of overloading. The weight capacity of a reciprocal walker is designed to sustain the user's weight without malfunctioning. So overloading can lead to instability, making the walker more prone to fall, injuries, and harder to control. So not only does overloading pose immediate risk to the user, but it also reduces the walker's lifespan. The added strain on its part can result in premature wear and tear, potential damage, or even breakage. So this places emphasis on the importance of selecting a reciprocal walker with an appropriate weight limit. So furthermore, incorrect weight distribution and unsustainable height can also contribute to discomfort and shaky footing, defeating the purpose of the reciprocal walker. So it's not just about the user safety, it's also about preserving the walker's integrity for a long term. Now, let's discuss another factor distributing to failure, which is also called as shearing stress. When forces are applied perpendicular to an object's surface, such as when a person leans one side or uses the walker on uneven terrain, shear stress is generated. The pressure exerted on the H-frame by shearing stress can lead to a reciprocal walker's failure. So using the reciprocal walker, right, by the bushing or the side frame instead of the H frame creates shearing stress. This stress can result in the frame bending, warping, or even breaking, making it really unsafe for the user. So despite the walker being designed to sustain user weight, the frame can flex or break under shear stress, rendering the device unsteady or even unstable. In addition, hand grips and bushing not made to bear such forces may fail due to shear stress. This could result in these components fracturing, ripping, or cracking, making the walker really uncomfortable. In essence, shear stress jeopardizes the reciprocal walker's stability by applying undue pressure to mechanical components, leading to bending, or warping, breaking, or even detachment, making the device challenging to control. And moving on, corrosion poses another threat to reciprocal walkers components. While aluminium, a common material for reciprocal walkers, is less prone to rust and can self-repair when damaged, corrosion can still occur under specific circumstances. So corrosion takes place when oxygen reacts with the metal's outer layer, creating an oxide coating. And so this coating, right, serves as a protective layer to prevent further corrosion. However, if there is damage to the oxide covering, corrosion may still occur. So continuous exposure to heat, salt, grease, moisture, or harmful chemical can cause aluminium to rust. Therefore, let's explore and discuss some solutions to these potential issues. So the choice of materials significantly influences a reciprocal walker's strength and durability. So materials like aluminium and steel have their own advantage and also limitation. In addition to material selection, the design of the frame is really crucial. A well thought out design ensures effective load distribution, minimizing stress concentration, and enhancing overall structural integrity. The arrangement of support bars and joints plays a key role in this. Furthermore, ensuring the robustness of load-bearing components is paramount. So regular checks for wear, fatigue, or damage in areas like the walker's leg is really essential. So prompt replacement or repair of components is crucial to maintaining the walker's structure integrity over time. So the quality of attachments such as hand grips, wheels, and even rubber tips cannot be overlooked. So these attachments plays a vital role as well in users' comfort and also safety. Same goes to what I've said just now. Regular inspection and timely replacement of any worn or damaged attachments are really necessary to ensure a secure connection between the walker and also the user, promoting a reliable and safe walking experience. And also to prevent corrosion, applying a fresh coat of paint can serve as a protective layer. So regular maintenance, including repainting when needed, not only enhances the appearance of the walker definitely, but also reinforces its structural resilience. So it's a simple yet effective measure to prolong the overall longevity of the walker. And to guarantee the best possible comfort and also safety, all fields should be measured for walkers. There are many types of walkers each with its pros and also cons. So for instance, right, the standard walker discussed in the report is ideal for those with balance issue, spending most of their time indoors. However, consulting with medical professionals is still essential for personalized recommendation based on individual needs. So as we conclude the discussion, it is important to highlight a few assumptions made during the report to ensure successful experimentation and also accurate calculation. So firstly, we assume that the reciprocal walker is in optimum condition, free from any damage or even worn out issues on its components. So this is to prevent variation in applied forces, as worn out or damaged part may lead to deviation from theoretical values. So additionally, we also assume that the forces applied to the reciprocal walker's components are in equilibrium, aligning with the principle of stability. A structure is considered is in equilibrium when all forces or moments acting upon it are balanced. Furthermore, we assume that the forces applied to the reciprocal walker are evenly distributed across its structure. So incorrect positioning or weight distribution by the user may lead to inaccuracies in force exertion, affecting the precision of calculation. So it's like any systematic errors related to measurement are closely or considered as neglectable. Over time, measuring tools such as tape measures may be slightly stretched, resulting in slight differences in dimension. Ignoring such errors, right, contributes to the accuracy of the experimental result. Lastly, we assume that the reciprocal walkers experiences no movement caused by wind or external forces to maintain a state of equilibrium. So assuming a stable state free from external influences is crucial for the accuracy of the experimental observation, adhering to Newton's first law.
And finally, for our report, I would like to conclude that this report has fulfilled objective of statics and mechanics of materials and also established a foundation for understanding and improving a biomechanical aspects. We also have advances biomedical engineering by emphasizing accuracy, safety, and user comfort. In the reciprocal walker overview, we have utilizes basic engineering principles for functionality and also put the diagrams aid in the understandings, balance, and loop problem solvings. In the real world scenarios, we acknowledge potential variation from assumed optimal conditions and also stresses continuous improvement in design of materials and user education. In the load distribution insights, we have the key information on load distribution, impact on the components, and internal moments unveil structure complexities. We also have emphasized the material strength and design by evaluate of shear stress on bolts for potential failure points and also stresses the importance of material strength and design in biomedical engineering. And lastly, we have put the biomedical device consideration into forces and bending effects on biomedical devices like the walker, and also emphasis on moments, inertia, and shear stress evaluation.